Hello, this is Nada. We are group 24, and we're gonna present the presentation number 4. And our group member is Neda, Karthik, and Paula. I'm gonna talk about KNN LR simple problem for real-time search. Independent of magnitude of the problem, real-time heuristic search and techniques satisfy a constant bound of the amount of planning per action. As a result, they are able to scale up the challenge, grow larger. The trade would make them ideal for video games where AI-controlled agents must react quickly to user input and activities of other agents. A novel algorithm, DLR CASR, has recently transformed the issue by attempting to remote learning by selecting thoughtful automation. The search for a path between two locations is typically issue in a video game. The real-time constraint drastically restricts the number of heuristic search methods that can be used in the situation. Real-time search takes a new approach to the problem. Real-time search methods compute only a few first actions for the agent to execute rather than computing a complete, possibly abstract answer before the first action is taken. CSR was the first real-time heuristic search method to incorporate this concept. CSR examines a state space in a pre-processing phase and generates a database of tuples which are then installed at runtime. CSR has a large memory footprint and sophisticated pre-processing module, and despite setting a new standard for real-time search, the resulting algorithm can be proven to be both real-time and comprehensive. I'm going to talk about subgoal database construction. Our goal is to keep DLR-CASR high performance while simplifying the algorithm and using memory constraints. DLR-CASR subgoal database uses the most RAM. DLR-CASR first abstract the map and using PRSR quick abstraction approach to create the database. Our runtime search, I would say any non-trivial map faces the problem of computing a subgoal for each curl space. As a result, the agent create a space and goals are rarely found in the database of subgoals. As a result, the agent will be unable to pick up its specific goal and will be forced to generalize from accessible data. A number of difficulties need to be addressed. The goal objective may be achievable via hill climbing from the agent's created state, but the agent may choose subgoal that takes its way away from it. This is addressed by determining if the global goal is accessible by hill climbing from the agent's current state. If that is the case, we will choose the subgoal selection and go straight for the global goal. Properties and empirical evaluation. KNN LRCA is both real-time and complete in the sense that it finds its objective in a limited period of time if the map is finite, and the goal is the same link component as the agent initial state. CNN LRCA outperforms DLRCA while utilizing significantly less RAM for its subcode database. For path finding in video games, the trade-off is appealing, especially on console, where memory is often scarce resource. This advantage comes at the cost of slightly longer pre-computation duration for constructing subcode of database and more complicated runtime models. As a conclusion, I would say the new algorithm KNN LRCA has several advantages for path-finding applications in the video game. Not only is its database computation easier to implement than DLRCA, but it also provides nearly a good runtime real-time performance while requiring significantly less memory for storing the subcode database. AI algorithms in video games should be simple to create and have a small memory footprint. And my team member, Owen, can start the presentation.
Yep, thank you, Nida. Good afternoon, everyone. So I will start with the introduction related to the learning real-time A-star path planner for the unmanned air vehicle target scanning. So it deals with the designing a fixed-wing UAV route planning approach that detects closely spaced ground objects and determines the optimum path while taking the UAV dynamic links. So this path planner deals with the shortest way is the best option for that reason we are going to learn about the real-time A-star. So we have the 5 methodologies related to path planning. So one starts with the learning real-time A-star search algorithm, vehicle limited turn radius, downwards looking center of fronting, and constant flying altitude and constant flight velocity. So when coming for the LRTS algorithm approaches, the parameters have a direct impact on the search running during path length performance. The route planning procedure must take into account not just the aircraft dynamics but also the motion of the sensor functions as an aircraft followed a predefined course. If the targets are far apart in the relation to the vehicle minimum turning radius, the path planning schedule is simple. The traditional path planning algorithms, on the other hand, not only well adapted for developing the pathway that efficiently uses the vehicle sensor functions with the objectives are close together. Now comes with the 3 technical challenges. So we have the technical challenges like, can go for the second slide. So we have the 3 technical challenges like coupling between the path segment, utilizing the sensor footprints, and third one is the determination of the view ordering of the targets. So so these are the 3 techniques which are part of figuring out the shortest way from the one target to the source target to the destination target. So the path segments that are optimal from one location to another location are a common strategy for the path segments. So these techniques for the multiple targets consist of creating ideal path from the beginning position to the first target, and from the first target to the second target, and so on it reaches to the destination target. The majority of the path planning methods generates the path that simply passes over the targets of the interest. So by this, many of the downward facing sensors used by a UAVs have a larger sensor function because seeing a target that does not usually flies directly over it. The purpose of path planning is to reduce the length of the path necessarily to observe all the targets. So next slide deals with the path segmentation. So in this path segmentation, coupling contains uh, two related to the path from the starting target 1 to the target 3. So we have the point-to-point optional path plan as well as the optimal multi-target path plan. So point-to-point optional path plan deals with the when an ideal path of the first target is planned, the vehicle direction as it flies over the first target place, it is a bad position to see the second target. In a similar way, the connection exists between the second path as well as second path to the third path and so on. So optimal multi-target path plan is clearly says that the path segment from the beginning location to the first target is longer than the ideal solution, which is placed in the figure of the figure A. But once completed, the vehicle is well positioned to observe the succeeded targets, resulting in a minimal path length for viewing all the objectives. So the next slide deals with the sensor footprint. So the sensor footprints of the is specified for the target that the sensor observes and affects the regular aspects of the target's orientation at the field location. So this sensor footprint also contains two figures which are pointing from starting point of the target A point to the target 3. So here we deal with the optimal path when viewing the target with the sensor footprint, and one more deals with the optional path when flying directly over the each target. If you look into the two figures which have been highlighted for the sensor footprint, the first diagram is showing the flying directly over the each target. In that it deals with the red dots with the targets and the blue dots with the optional path. The second diagram shows the sensor footprint to view the targets. The green boxes which are highlighted in the second diagram gives the sensor footprint. So however, much shorter the path is the when the sensor footprints are used to view the targets. So the next slide deals with the target viewing order determination. So viewing order determination is similar to the traveling a salesman problem, which is known to be a NP order. The path planning issues covered here have the extra complexity of a restricted turn radius and sensor footprint to exploit in addition to the settings of the viewing order. Due to the difficulties of this, it works well only at the constant altitude and the velocity flying using a downstream pointing sensor. As a successful path planning strategy for viewing the closely spaced objects from a UAV necessitates the following skills in a planner, like utilizing the whole sensor footprints to observe the targets and determine the viewing order of the objects, providing the minimal length path. And the next slide deals with the build the tree of flyable paths. So this tree has a total of 40 nodes. As you see on the right side, we have a figure. So it contains the 40 nodes followed by the depth of 3. The node destination will be the P of x of 5, flag. So each node has a children nodes as a C set, target sensor as S set, and target nodes as P set, and for all we have a one parent node as P. So if you look into this diagram related to the tree of flyable path, the flow will be it will travel in a straight segment way. It travels it turns from the right at the smallest vehicle turning radius, and one that turns left at the smallest vehicle turning radius. Until we construct a tree of flying path, the speed which will be the best path is found is affected by the segment length and the tree depth. The memory space for this is also a concern, and according to the reading materials, tree depth for the desktop CPUs should not exceed more than 30 to 50 levels. So the next slide deals with the LRTA star and how it works and also the initial heuristic. So learning real time A star is very much slower than the A star, and it contains less memory space than the A star, and each node has a H. So your H indicates the heuristic, and it contains the distance to view all the unnecessary targets. And at the each step of this LR2A star, current node computes as a F. So your F relates to the current node EST, and remaining travels is chosen based on the child C. So current node updates its own H with the minimal F function when considering all its children. So current node can be the child seed that yielded the main function F, and search contains to move down tree until all targets visits or path is longer than the current best path. And LRTA star at the each path search always starts from the root node, and this algorithm stops when there is no improvement made over the total heuristic. So the next slides will be continued from my team member Karthik, and he is going to start with the branching terminals. Thank you.
Karthik, you're mute.
Hey, good afternoon all. My name is Karthik, and I'm going to start from my part. It's like branch terminal, memory management, and path tree terminals are critical for the LRTA tree search to operate well. In all of them, node children like hesitate values of infinity, the node is at that end and have been terminated in the same way. Where if at the given node H plus found DS discontinued DS, like the following figure shows the planning path of LRTA and NLR algorithm. Moving to the next slide, like path tree size. Like the size of the path tree is a key issue while searching it. The whole root tree is 3D in shape, where D is the number of levels in the tree. This means that for a tree 30 levels, they are approximately 3.1 into 1014 nodes. The size of the tree with 30 levels is 5.42 into 1010 nodes, which is less than 0.02% of the size of the whole root tree. And moving to the next slide. State size selection. The genuine global optimum would be found in the state size in the LRTA tree. State would reduce to an incredibly small value. The LRTA router plan currently uses a state size DS, like maximum tree depth determined by sparing the valuable path length and fixed state size. The greater depth and starting possible path length might be used to calculate the latest flexible step size. Moving to the next slide, testing and comparison. The LRTA and NLRTA algorithms tested on 2000 target situations produced from a R2RT by 2RT globe. The tests were carried out on an Athlon XP 1500 plus and 1.33 GHz with 512 MB RAM running Linux. The NLRTA algorithm requires 10,000 rounds of no improvement. The experiments involve 0.2 into 0.65 random step sizes in 0.05 radian increments. Moving to the next slide, like LRTA tree set validation. The highlight the LRTA tree set benefits the path created by the algorithm, which compared to the path obtained by a brute force global set using dozen paths. The LRTA algorithm sensor footprints was decreased to match the vehicle traveling through the target spot. The following figure shows that LRTA sensor footprint closely approximates the best path found through the global set, and LRTA uses a large sensor footprint to reduce travel length by 33%. path length. The path length approaches allows each ray to contribute to every region it crosses, increasing speed and statistical correctness. The mean trip length rises by nearly 19% over the step size, range demonstrating the smaller steps are preferable. The mean path length increases by just 6.8% between 0.2 and 0.4 radians, demonstrating the declining value of the smaller step sizes running time. To convey running time data in a platform independent manner, the number of nodes visited by the step is used to specify the running time of an algorithm. Based on the image given next to this, at a step 0 size of 0.3 radians, the LRTA algorithm means running time lower to around 200 nodes of 0.5 as a 98% reduction. For the NI LRTA node, the execution time is reduced by 47% to around 80,000 nodes, like 0.15 seconds. Different number of targets. 2,000 random target situations are utilized for each number of targets for 1 and 8. Using a step size for the rest of 0.25 radians to evaluate the algorithm's performance for varying number of targets. The LRTA algorithm visits an average of 5.5 million nodes, 70s for 8 targets, whereas the NI-LRTA method visits an average of 200,000 nodes to 0.5 seconds. For whatever number of targets, the NI-LRTA method is consequently quicker than LRTA algorithm. Conclusion: the LRTA and NI-LRTA research algorithms are presented in this paper, which locates the branch for a discrete step. Route 3, the best achievements a set of specified objects. The LRTA algorithm is guaranteed to yield the shortest path, although it takes longer to run. The NLRTA algorithm successfully trades off from path length, performing in exchange for significant quicker running time by avoiding the effects of coupling between path segments. The LRTA and NI-LRTA algorithms plan optimum or near optimal pathways in various objects. This is our concept. Do you have any doubts?
Thank you, guys.
Thank you so much.